record. Okay. Okay, so now let's quickly go through what we have learned in last class. In previous class, let me see. Let me double check if I'm recording to make sure we are recording. Okay, yes, we're recording. Okay, so from last class, we have learned one important concept, which is pressure. So if you remember, what is pressure? Actually, it is the force over area. So it's the ratio of force and area. And the way to calculate the pressure in a fluid is simple. It's just this equation. P is the pressure of a liquid. P0, it's the pressure of the atmosphere. And rho is the density of the liquid or your fluid. And G is the gravity constant. D is a depth. So the equation is very simple. P equals to P0 plus rho G D. The way to derive this equation has been shown in last class. If you forget it, you can read this slide again. It's very simple because the pressure of a liquid or fluid is generated by gravity or the weight of the liquid above some point. So you can simply calculate it with rho G D. And this is a way of calculating pressure. Today, we're going to use this equation and two important rules to do some more complicated but interesting calculations, which you can use in many daily life situations. First, let's introduce two important rules for liquids. The pressure in liquids. Now, let's see the two simple and important rules. Number one, a connected liquid in hydrostatic equilibrium rises to, sorry, someone is asking a question. Let me check. Okay. Okay, so someone is just sending a message, say there's something wrong with the dorm. So it's okay. Now let's continue to the two rules. Number one, a connected liquid in hydrostatic equilibrium rises to the same height in all open region of the container. So for example, you see two containers A and B. In situation A, the two, actually in this container, there are two tubes, one narrow tube and one wider tube. If you put some liquid in, is it possible that D1 is greater than D2? Actually, it's impossible. If you do an experiment, we cannot do it by this time, but you can imagine if this is an experiment, when you put some fluid or water in the container, D1 will always equal to D2 because they always keep the level to be the same as the horizontal level. So rule number two, in hydrostatic equilibrium, the pressure is the same at all points on the horizontal line through a connected liquid of a single kind. Here, in let's say in figure B, we have two actually containers connected by some tubes at the bottom, a cone and a tube. if we choose 2 points, 1 and 2, and we measure the P1 and P2, so which pressure is higher, P1 or P2? If we do the experiment, if we measure it, we will see P1 equals P2. No matter what the shape it is, if P1 and P2, they are at the same level, or if they're on the horizontal line, then the pressure should always be the same. If the liquid is the same kind, and if the, let's say, if there's no mixture of 2 or more liquid, then at the horizontal line, the pressure is always the same. Actually, you can use the rule number 2 to explain rule number 1, because if you see in figure A, why it's impossible? Because, okay, let me draw something. Because if you consider the pressure, okay, if you consider the pressure at position A and the position B, what happened is because the liquid is the same kind, so the pressure A should equal to pressure B according to the rule number 2. But if D1 doesn't equal to D2, then the pressure at A cannot equal to pressure at B, because if you calculate the pressure at B, it equals to P0 plus rho G D, because there's some liquid above B, and then A doesn't equal to B, so it's impossible. So the height of B will go down and the height of A will go up. Finally, they should be at the same level. So that number 2 of the rule should be true. Okay. Now, if you understand the rule number 1 and the rule number 2 for liquid, now let's see this question. So which option do you think is correct? A, B, or C? Please type your answer via the chat. So can you see my chat window? Actually, I shared the screen, and for sure you can see my slides. But for the Zoom software, now I'm opening a chat window so that I can check your answers. But are you able to see my chat window? Or you just see the slides? Okay, no, so you cannot see my chat window. That's good. So I'm the only one who can see all the answers. So you just type your answers without any, without checking others' answers. Oh, you see everyone's message. Okay, then okay, it's fine. So don't see others' answers. Just make your own choice. So far, I see 4 of you have chosen B, and 3 of you choose A. Actually, the correct answer is B, because no matter if there's an iceberg or something above the position 1, but based on the rule number 2, if the point 1 and 2, they're at the same level or at the horizontal line, and the liquid is the same kind, in this situation, the liquid is water, it's the same kind, then the pressure should be the same. Hydrostatic pressure is the same at all points on the horizontal line through a connected fluid. That's the rule number 1. Okay, now let's see next question. So which pressure is higher, P1 or P2? Please make your choice in the chat window. Great. So this time I see most of you, actually so far all of you choose the right answer. Okay, great. Yes, the answer is C. They equal to each other. Still, the rule number 2, they're at the same level or the same horizontal line, so they should have the same pressure. But let's go back and see the rules. Be careful that when we use the rule number 2, it said it's a connected liquid of single kind. If it's not a single kind, then things turns more complicated. Now let's try to solve another problem. So there's the water fills the tube shown in this figure. What's the pressure at the top of the closed end? So the pressure here. Okay, so first, this is a liquid in hydrostatic equilibrium, and this is a single kind liquid. It's just water, so there's no mixture of 2 or more different liquid. So the rule number 2 is true. Then what we can do is, if we want to calculate the pressure here, if we want to calculate the pressure here, it's the same thing for us to calculate the pressure at the left. And it's much easier for us to calculate the pressure at the left because we can use rho GH or rho GD to calculate the pressure generated by the water bar above this position. And then that's the pressure. Now I need to clear the drawing and go back. Okay, so the way is the P equals to P0 plus rho GD. D is D is the height above the horizontal line, which is 100 subtracted by 40 centimeter. Then rho, of course, is the density of water. G is 9.8. So you can calculate the pressure here. So that's an easy task. Okay, now let's quickly go through another test. What can you say about the pressure at point 1, 2, and 3? Now you have 5 options. Please type your answer in the chat window. So which one is correct? Or if you think all of them are wrong, what should be the right answer? Okay, now let's see. So great. I see some of you have typed some answers. Great, great. Yeah. So now let's see. So first of all, if we compare point 2 and 3, do they have the same pressure? The answer is yes. 2 and 3, they are at the same horizontal line, and this is the same kind of liquid. So P2 equals to P3. Now let's compare P1 and P2. Do they have the same pressure? Of course, no. We have learned the deeper in the liquid, the higher pressure it gains. So P2 is greater than P1. So the answer should be P2 equals to P3 and P2 is greater than P1. So there's no right answer. The answer is wrong. Don't look at the wrong answer. Okay, now Pascal's principle. If the pressure at one point in an incompressible fluid is changed, the pressure at every other point in the fluid changes by the same amount. We'll use this principle in the future. Now let's introduce a little bit about. Okay. Oh, there's something wrong with my slides. Okay, now let's look at the atmospheric pressure. So on Earth, there's a gas. So there's air. So gas is compressible. So the air in the atmosphere becomes less dense with increasing altitude. So for example, this is the Earth. And if we consider the density of air, you will find that at the bottom of the Earth, the air's density is higher and the pressure is higher. And when we go up, due to the gravity of the air, when we go up, the density and the pressure of air becomes less and less. And 99% of the air in our atmosphere is below 30 kilometers. And atmospheric pressure varies with altitude and with change in the weather. And now next section, how to measure and use pressure. Manometers and barometers. A manometer measures gas pressure. So here's a manometer. This picture shows how the manometer works to measure the pressure of gas. So for example, if you have some gas in this box and you want to measure the pressure of the gas in the box, what we can do is we can use a tube, and this tube is filled with liquid. Usually it's a mercury because mercury has a very high density compared to other fluid. Since the pressure on the horizontal line are equal, so if you check the pressure at P1 and P2, actually P1 and P2, they have the same pressure because they're at the same horizontal line. And P2 can be calculated by rho GH. Rho is the density of the mercury. H is the height of this liquid bar. And then you can calculate the pressure at P2, which is P0 plus rho GH. P0 is the atmospherical pressure, or 1 atm, means the.
You have to memorize each one. Because like you have chi squared, you have like
Chi squared.
Yep.
I can hear someone is talking, discussing some homework or something? So let me mute everyone. Okay, now everyone is muted except me. So this is a way to calculate P2, and P2 equals to P1. P1 is the pressure for the gas. So by using this device, you can calculate the pressure for gas. This is called manometer. Now let's see another way to measure the pressure, which is barometer. A barometer measures atmospheric pressure by putting some liquid in a glass tube, and then you put the glass, or you place the glass in the beaker of the same liquid in this way. Some, but not all of the liquid leaves the tube. And then there will be some vacuum above the liquid, and then there's a liquid bar. So vacuum doesn't generate any pressure, but the atmospheric, if we measure it on ground, we know there's atmospheric pressure which is pressing the liquid here. And we know at the position 1 you have atmospheric pressure, and at the point 2 you have the pressure of the liquid, which is calculated by rho gh, and rho gh equals to the atmospheric pressure, because P1 equals to P2 because they're at the same horizontal line. And then P equals to rho gh. This is the way to calculate or to measure the atmospheric pressure. And this is barometer. Okay, now let's try to solve a more complicated problem. A U-shaped tube is closed at one end, at P3. The other end is open to P0, or to the atmosphere. Water fills the side of the tube that includes the closed end, while oil floating on the water fills the side of the open tube to the atmosphere. The two liquids do not mix because water and oil, they don't mix. They do not mix. The height of the oil above the point where the two liquids touch is 75 centimeter, while the height of the closed end of the tube above is 25 centimeter. What is the gauge pressure at the closed end, or what is the pressure at the closed end? So first of all, let's ask a question. Does P3 equals to PA? Is that true? Does PA at this point equals to P3 at that point? Or another question is P1, P2 the same? Does P1 equals to P2? So for P1 and P2, it's simple. P1 equals to P2 because they're at the same horizontal line. But PA doesn't equal P3 because even though they're at the same horizontal line, but it's not the single kind fluid. There's some oil at PA, but here are some water at P3. So they don't equal to each other. So that makes the calculation more complicated. But one thing we know is P1 equals to P2. And we can calculate P1 easily. it's rho GD, and rho is the rho 0, which is a density of oil, and D is the depth, which is 75 centimeter. We can calculate P1, then we know P2, because P1 equals to P2. But we want to calculate the pressure at P3. So let's say P3 is a pressure generated by the closed end of the tube here, plus the pressure generated by 25 centimeters of water equals to P2. So if we draw a picture here, what we can see is at this point, you have P3 pointing down, and then you have P, let's say, generated by water, which is also going down. And then you have P2, which is going up. And you know P2 equals to P1, it can be calculated by rho GD of oil. And P water, it can be calculated by this much of water. It's rho GD. Rho is the rho of water, D is the depth of water, it's 25 centimeters plus P3. And we want to calculate P3. You can calculate P2, you can calculate P water, then P3 equals to P2 subtracted by P water. So that's the way of calculating the P3. Okay, so first, let's calculating P1. So P1 equals to P0 plus rho GH. Rho is oil density, H is 75. Then you calculated P1. Now let's calculate P2. So P2 equals to P3 plus P water, let's say, the pressure generated by 25 centimeter water. So P water equals to rho, actually rho W means rho of water, density of water, rho GD, D is 25. So P2 equals to rho water times G times D. P2 has been calculated in previous equation here because P1 equals P2. This is P1, this is also P2. P2 has been calculated and P water has been calculated here. The only thing you don't know is P3. So P3 equals to P2 subtracted by P water. And then you can calculate the P3. It's shown here. Okay, so that's the way of calculating this complicated pressure at the closed end. And here are some pressure unit. Pascal. So the most commonly used pressure unit for pressure is Pascal. The abbreviation is PA. So one atmospherical pressure equals to 101.3 kilopascal. So actually, Pascal is relative small number or small unit, but atmospherical or one atmosphere or one ATM, it's a very big unit for pressure. So 1 Pascal equals to 1 Newton per meter squared. So it's most used unit in SI units. So Pascal. Blood pressure. So blood pressure is measured by pressurizing a cuff around patient's arm. And I think everyone has used this device to measure your blood pressure. So it's easily to understand the mechanism of this little device. But the question is, when a doctor or nurse give you the blood pressure, the first number is systolic blood pressure, and the second number is diastolic pressure, or the high pressure and low pressure. And the one thing you may notice is that when they measure your pressure, the patient's arm is always held at the same height or same level as the patient's heart. So why is that? So when you measure the heart pressure, can you raise your arm up or lower your arm down compared to the level of your heart? The answer is no, you can't do that because that will result in a inaccurate pressure. The hydrostatic pressure of a fluid varies with height. So even though the blood is not hydrostatic equilibrium, but still it's true that the blood pressure increases with the distance below the heart and decreases when it's above the heart. So the upper arm besides the body is at the same height as the heart. The pressure here is almost the same as the pressure at the heart. So if the patient held the arm straight up, the pressure cuff would be a distance of at least 25 centimeter above the heart, and the pressure will be less. And it will cause a huge error. And this error can result into let's say, an error in the diagnosis. So when you measure the heart pressure, so make sure your upper arm is always at the level of your heart. That makes the measurement more accurate. Okay, that's all for today's class. In next lecture, we're going to learn buoyancy. Do you have any questions about today's class? If no questions, that's all for today. I'll see you on next class, which is Monday. See you on Monday. Bye-bye.